Yeah, hello everyone. So I guess I'll be just yelling a little bit so you guys can hear me. Let me know if it's not enough. We're just going to build on the momentum that we already have in this excellent series of talks and just dive right into language modeling for chemistry, guys. I'm Philipp as well, not Seidel, but Guevorguian, and I'm with YerevaNN. So I want to actually start by first thanking all of my peers and colleagues that work with me there, as without them I wouldn't have anything to present. And of course, biggest thanks goes out to all of you who are here watching me. So at YerevaNN, we're actually very interested in the interaction between machine learning and the chemical domain. So we're going to look at both what kind of utility these molecular language models provide for chemistry, but also the vice versa. What can the chemistry domain and those problem settings provide in terms of insights into language modeling in general? And we're going to start that right away after this introduction, looking at a unique metric that can really only be meaningfully calculated and interpreted in this molecular generation task setting. Then we're going to look at BART Smiles, a recently finished project where we basically took a larger scale training regimen, larger scale model, and looked at what kind of results it could get on a variety of chemistry domain tasks. In that, we're also going to have a look at what exactly about chemistry does a large language model come to understand after successful training. And at the very end, we're going to talk about how using multiple modalities can extend and basically empower these large language models to perform on these tasks. Then we're going to wrap up, and out of kind of consideration for our own lunch, we are going to have 5 minutes for questions. So I promised some unique metrics. So if we have a regular English language model, we can, for example, ask it to describe this beautiful scene here, this waterfall cave forest combination. And I really did this, so I got these responses here. And then to, for example, calculate the precision of these responses, it would be relatively straightforward, assuming we had dedicated enough interns and or graduate students. So we can play that role here today. Say, yeah, this is correct, this is correct, this is incorrect. And so that gives us our precision of about 0.66 repeated, whatever. But if we wanted to calculate recall, we actually couldn't do that because we don't have the denominator. We haven't enumerated all of the possible sentences that exist in the world that describe this scene. But in the molecular language, the situation is a little bit different. Okay, we have this kind of molecular space of 10 to the 60 drug-like molecules. And within that is a subspace that's represented by a perhaps industrially underappreciated data set called GDB13, which contains virtually all of the molecules that contain 13 or less heavy atoms. So within that data set, you can see we have kind of these smaller molecules, and outside in the black, we have these bigger molecules. So it contains all of them, and we could theoretically kind of get this as our training data set, these 1 billion molecules, or a subset, and see how well it could recover that space. Now, how are we going to do that? So we have kind of a few options here in terms of representing this molecule. This is aspirin, which I like to use for engineering-related headaches. And there's a few ways. So the first option is to use SMILES, which is a linearized string representation. Basically, we take our molecular graph, turn it into a line, and convert it into a string. And for example, aspirin has a few of these. And the one thing to note here is that if you don't follow the SMILES construction rules, you might end up with an invalid molecule. So that's something to keep in mind. But for selfies, they're kind of similar. They can also be arranged in different ways. They're a bit longer and have a more expansive vocabulary. But they do solve that construction rule issue, as every combination of this relatively expansive vocabulary in selfies is guaranteed to always return or correspond to a valid molecule. Cool. So given that this is our set, we could, again, sample from this, train on it, and try to recover this full set. Or we could do something that's of greater interest to people working in the chemistry domain, doing the applied work. And that might be to ask the model to recover for us a subset of these molecules that has certain verifiable and desirable properties. Okay, so I have the number at about 8 million here because we've chosen two different subsets to look at. The first being those molecules which are synthesizable, okay, meaning easy to make in the lab. And the second being drug-like. So remember aspirin? Those molecules which are similar to aspirin. Now, it's key to note here that we can actually calculate this trivially and deterministically. So we can actually filter all of GDB13 to create these kind of ground truth subsets. Then we can get another subset of that as our training set, randomly sampled from our subset, and see for each of these independent subsets, we can train, let's say in our case, an OPT autoregressive model, GPT-like, and ask it to recover those subsets. Try to learn a uniform distribution over that subset data. Now, what's interesting about that is by doing this, you can measure how hard it is for the model to learn the task, but more specifically, the intrinsic difficulty of characterizing the space. So we do exactly that. We train those models, and we ask for 100,000 molecules generated from each of them under varying sampling parameters. So we're going to start simple here, guys, only looking at the GDB space in total. And we're going to have the red line here representing the unique count on the y-axis, right? We're looking to evaluate recall, so we're not going to allow duplicates. The blue line is for those molecules generated which are in GDB, okay? So in this case, this is our recall. Now, on the x-axis, we have the top P probability. This is a fancy nucleus sampling parameter that basically means as it increases, the diversity of the molecules generated increases as well. So with that being said, it kind of makes sense that as we increase that diversity, we're allowing the model to go outside of that GDB space. That's intuitive, right? Because we can then generate molecules with greater than 13 heavy atoms. Okay. And again, we have smiles on the left, selfies on the right. So something to keep in mind. Now, to make it a little bit more complicated here, we have smiles on the left again, selfies on the right. On the top row, we have that aspirin-like subset. On the bottom row, we have that synthesizable subset. And you notice we've added also here two lines, green being the unique count that meets that subset's criteria. So we go look at those 100,000 molecules generated and see how many of those, computationally, we check by ourselves, if they met that criteria. Now, purple is actually what we're most interested in here, as that's our real recall. These are the molecules which both satisfy our criteria, but also are in GDB13, meaning they would be a part of that original subset or two subsets that I discussed earlier. And there's kind of two things you can notice here. The first is that, unlike on the previous slide, where at lower top P probabilities, we kind of had a flat line, here, where the top P is lower, we're also getting lower unique counts. And the reason for that is that we're then, by constraining the diversity of molecules generated, kind of allowing our model to create more and more duplicates in this case, because these subsets that we're training on, or sampling from and training on, are much smaller than the full GDB space, right? So that makes sense. And another insight here is that given that that purple line is what we're interested in, we can see that the ideal molecular representation may actually be task-specific. So here on the left, smiles is performing better for the aspirin subset, and selfies are performing better for the synthesizability subset. Now, we then actually found that the recall there wasn't super high, given we're only generating 100,000 molecules, because as time goes on, as you generate more, you're more likely to see duplicates. So here, what we did was we dropped that top P parameter to allow our models full diversity. And then we took larger and larger models. So on the x-axis, we have from left to right, 800,000, 85 million, 302 million, 680 million, and 1.2 billion parameter models. And wanted to see how the size of the model actually impacts its ability to recover or characterize these spaces. And we found that kind of our most interesting subplot here is the bottom right, which is basically our recall. And we find that as model size increases, the recall does in fact increase. And this really speaks to the quality of these selfies representations, as if the representations didn't have sufficient data to characterize the space, increasing and increasing the model size wouldn't have any effect. So this is where we're at with that. This is a relatively novel and niche analysis, but it was actually inspired by work that we were working on last year by the name of BART smiles. So this is kind of a separate project where we trained a large BART, right, mass language modeling transformer on 2 billion molecules this time from zinc, so a different data set. And we trained it for about 20,000 GPU hours, which this scale ended up actually making a difference as we saw a 5 absolute point increase over training on, say, 5% of the data. So after the pre-training, we then fine-tuned for a variety of prediction and generative tasks. And at the end, we'll also do some interesting attribution and interpretability analyses as well. So just to recap, for BART, we're giving it these molecular string representations, just masking them, denoising them. And then for every individual task, we have to do a task-specific fine-tuning, so more training. And for the results here, we're going to start with a regression. This is a prediction task. And we have here eSolve, FreeSolve, and lipophilicity from the famous MoleculeNet benchmarks. eSolve and FreeSolve basically relating to how soluble the molecule was found to be in a variety of experimental results. Okay, and lipophilicity is basically how much the molecule likes fat. So again, very similar to solubility, or a proxy measure, if you will. And through these results, we find that BART smiles perform state-of-the-art when compared with traditional machine learning methods, graph neural networks, convolutional graph neural networks, as well as a litany in that last row, part of chemical molecular language models. Okay? Then for the generative tasks, we looked at retrosynthesis, which the other Philipp kindly explained for me, but I will mention again. It's giving a molecule and asking what we needed to have in advance in order to synthesize it. So here we find that we measure the top k, which means that we query the model k times and check if the correct answer is in those k responses, and then measure that accuracy. So we find that for top 1, we outperform all the baselines, but for top 5 and top 10, the augmented transformer 100 augmentations model, which does some interesting pre-processing on the data, does perform better. But what exactly is this model? Oh, by the way, I should mention this is taken from US patented chemical reaction data set, so very standard. And what exactly does this model come to understand when it is training? So there's actually a very nice data set where chemistry domain experts were given toxic molecules, so maybe if you drink them, like you'll die or something, and they were tasked with identifying the substructures in those molecules which contribute the most to their toxicity. Okay, so that's what we're seeing here. So we have here a nitrogen with 2 oxygens, another nitrogen with 2 oxygens, and some ring structures. So if you know chemistry, you might already understand why this is. But what about our model? So we can see here, these are the strings that our model is actually looking at, for example, here. And we have a highlighted region here. We have some highlighted regions here. And actually, if we plot them in an image, we can see that the corresponding atoms that our model selected were congruent with what the domain experts selected. Now, the way we did this is by using the integrated gradients method in order to check what part of the input the model disproportionately was attending to during its prediction. Now, keep in mind, this is, of course, a fine-tuned model, right? This is a fine-tuned model. So there kind of is a gap here, right? There kind of is a gap. Because after this relatively expensive pre-training on these molecular string representations, for every single one of those tasks, we have to fine-tune. And that brings us to what we're working on now, ChemLactica. So in addition to these molecular string representations, we now take various textual information about the molecules from PubChem in order to skip that fine-tuning step, allowing the model to solve all of those tasks, deal with all of those tasks without that computationally inefficient, data inefficient fine-tuning step. And so we actually generated a relational database in structured text format that allows us to organize this data in a variety of formats, whether that be for all of the different molecules, all of the data that corresponds to a given molecule, or for a given experiment, maybe all of the molecules that had a certain result on that experiment. But this is what we ended up coming up with. Right. So this is our data here. You'll see in the top row we have, of course, our smiles, our favorite. And then on the second row, we have a variety of computed properties. So the number of rings in the molecule, the molecular weight of the molecule, and of course, that synthesizable score that I discussed earlier. Then we are kind of now adding more novel information from PubChem. This is the result of a solubility experiment. This is the result of a dissociation experiment. And then we introduce also molecules that are similar to our query molecule, as well as assay data from PubChem. So Philipp already kind of discussed a lot about these, and we include, as he mentioned, those assay names and assay descriptions, as well as the individual variable names and descriptions for every individual measurement taken in that bioassay, as well as the corresponding unit. So what does this allow us to do? This would allow us to give a molecule, and ask for that SAS score, right? So you have the smiles, what is the SAS score? Or what is the result, or what would be the result of a solubility experiment on this molecule? And my favorite is, assuming all of this other data, what is the molecule that corresponds to all of this, right? So we have all of that. And we actually, in our preliminary work, have done something similar. And at the top, you'll see how we actually prompt it. So QED is quantitative estimated drug likeness. It's basically a computed property that's relatively complex, combining several factors from the molecule to guess or to kind of describe how drug-like it is. So we prompt it with a given number. Then we say, hey, give us the smiles. And so on the x-axis here, that is what we're prompting with. On the y-axis, once we return the model's response, we actually go and we calculate that value. And then we plot them against each other. So this is the 125 million Galactica model trained on that method that I just described. And we're getting here a relatively good result with this Spearman correlation of 0.734, which we've seen recently in other papers, similar results reported on a more inductive biased kind of used method. And so we have that, which kind of describes that it tells us that this model is able to learn QED, and furthermore, it's able to learn the rules of generating smiles without making mistakes. So we hope to use our kind of robust training schedule and regimen and data format to do this kind of analysis on more complicated properties than, say, QED, and also using it to optimize multiple properties at once, which is a unique kind of advantage of our approach, is that we can ask for QED, another property, a third property, and then do that kind of valuation. So that's what we're looking to do. So we went over a lot today, guys. I want to thank you. We talked about the ability to use this chemistry domain to calculate specific new metrics in language modeling in general to understand how they work, as well as what a large-scale model can do, as well as what specifically in chemistry it has come to understand after fine-tuning. And finally, how you can use multiple modalities to broaden the range of tasks it can do without having to sacrifice that computational efficiency. So thank you all very much for listening, and I will now take questions.
Aren't you concerned with chemical weapons?
Am I concerned about chemical weapons? Yes.
Yeah, about chemical weapons, because it enables to accessible and distribution of the knowledge to make it large-scale attacks of bad actors accessible with these language models in synthetic biology and chemistry as well.
Absolutely. So currently we're kind of in the preliminary phases of our work, but I mean, if you look at, if we find that we are able to get to that point where we can kind of accurately design chemical weapons, we'll do something similar to, first of all, the project is currently closed, but if we do choose to open this up to the public, we can do something similar to what OpenAI has done, which is, you know, if you currently try to query OpenAI for any kind of risky molecules, then you won't have any luck. So maybe we can do that kind of an approach, but we currently are not even at that phase yet to be kind of worried about that. But yes, definitely. Yes.
Yeah, Awesome work, thanks. When will this work be published? What's the timeline?
It's hard to say. It's hard to say. Hopefully within the next year, I would say, yeah, we would like to get this published. It really comes down to how much of these experiments we want to do before we publish, or we want to kind of turn into 2 or 3 papers, because again, our model kind of is quite flexible. So there's a lot of different options for evaluations if you have any ideas. But yeah, ideally within a year.
Two
Yes,
quick
I
questions.
see.
I've seen you used smiles, but at the beginning you alluded to using the selfies. But
Yes.
Then you used smiles, right?
Yes. We use smiles in the Galactica part.
Yes.
Yes, so the reason we chose to use... Yes, perfect. Okay, so the reason we chose to use smiles for the Galactica is because Galactica has actually already seen, not many, it hasn't seen many, I think about 2 million in the initial Galactica publication, but it has seen some smiles already tagged in this way. So we just took these tags and used smiles again for consistency with the pre-training of the base Galactica. Right? For our other project with the recall calculations, we're playing with both smiles and selfies, as well as actually a few other augmentations like the randomized smiles, if you've seen those, yes. So that's why, just for consistency with Galactica, that's the only reason really.
One more question,
Yes.
and then we'll ask the others offline. So
Yes.
when you fine-tune or have a lot of tasks, usually what you observe is that some tasks get worse, or it's not very optimal. Have you observed this, or did you deal with any of those issues?
Yes, so we actually have kind of an interesting training regimen where we try to calculate the perplexity. We try to calculate the perplexity for every individual property that we're looking at. But I can't say that and we do see variations there during our training, but I can't say that I'm confident enough in the kind of variety of our evaluations to say now. But yes, I do assume that'll be a problem, or especially if I say, let's give me 3 properties and then give a molecule, that'll be much, much harder. So that is something we have to consider. Thank you. And yes, offline.
One more comment about your first question, when and what to publish. So, one important bottleneck here is the compute, because you have all sizes of Galactica, and the data that it's possible to get from PubChem is large enough for even the larger ones, and it's not clear when we will have access to that amount of compute to do that. So maybe at some point we will give up, or maybe we will
Cut it short.
compute then. Yeah.
Which size of Galactica are you using?
Now we started from
125
million. It's now 1 billion is training. I think we can go to one more level at least, but yeah. And then the other question is, which is still an open discussion. So this is like very generic. It can solve like if you're looking at regular language models, they do evaluation of like hundreds of tasks, right? Sometimes, and it's a big problem to decide on which you want to evaluate, on which you don't, and where you should stop, right? Because it could infinitely go. So one option is to do on a couple of popular things and then give it to the community so that everyone can find new applications of this, right? But maybe if we find something interesting, we can dive more into it before releasing. So these are the trade-offs.
So if you publish the main model, maybe you can decentralize the learning and combine the results together.
Let's talk about it. I don't believe in decentralized training, but maybe I don't know something that you know. So we can discuss it. Thank you.